Hello everyone, welcome to lesson 1 for AB Calculus. This lesson's on infinite limits and limits at infinity. I will just say that this very first example that we have is just a quick review from what you should have learned in Algebra 2 and pre-calculus. So I went ahead and did all the little grading work that needs to be done just so you guys can get an idea of what this function looks like graphically. So I'm going to take a little minute here and just kind of talk about what I did and how I was able to get these things, just as a quick refresher for us if we need that little pre-calc reminder. So the first thing that I did is I factored, right? So I pulled out a 3, it was x squared minus 4, so then I realized that was a difference of 2 squares, so I did x squared minus 4 is x plus 2 and x minus 2. I took a 2 out of here, and that left x squared plus 5x plus 6, so then I was able to factor that to x plus 2, x plus 3. And then I was able to cancel x plus 2 from the top and from the bottom. So right here, this lets me know that there is a hole in the graph, this function, at x equals -2. And so then I plugged in -2 here, and I got -1/6 as my value. So that's how I have a hole right here in the spot. All right, so that's the first thing I did. And so once I got to this point, then I realized, okay, well, the denominator, if I set the denominator equal to 0, that's going to give me my vertical asymptotes, right? That's the vertical asymptotes that you guys do. Well, the 3 doesn't matter, so when I set x minus 2 equals 0 and x equals 2, and by the way, if you guys notice, just to make this easier on the eyes, I decided to make every 3 a 1, right? So every 3 lines is 1, 2, 3, 1, 2, 3. So at x equals 2, right, at x equals 2, I have a vertical asymptote. The numerator does not give you the horizontal asymptotes. Remember, the numerator, that gives you your zeros. That gives you what your zeros are. So if you set this equal to 0, you get a 0 at x equals -3. We do not include this one because, again, this is a hole, so it cancels out. Then the next thing that I did is I looked at my y-intercept. Remember, for the y-intercept, all your x values are 0, so this, and this go away. I have 12 over -12, which ends up being -1, so I was able to get that 0 right there. And then the one thing that we kind of have to remember about this is our friend, the horizontal asymptote. And so this is the kind of conversation that we're going to have now, because remember that for horizontal asymptotes for rational functions, you look at the highest degree of the numerator and you look at the highest degree of the denominator. In this case, we chose a very simplistic one for you. They are equal to each other. So the degree of your numerator, the highest degree is 2, right? This is the degree of 2, 1, and 0. The highest degree in your denominator is also 2. So since that's the case, then what you're going to do is you're going to take the ratio of your constants and you're going to get the equation y equals 2/3. Again, I made this 3 so that way I can draw that line very easily to you. And then all you have to do is just connect the dots, right? I always say to students when I taught pre-calculus that the zeros and your y-intercepts, those are the doors to get you through the lines. So that's the way that you're able to get through these lines. And then the asymptotes, usually you don't cross them. I mean, sometimes you cross the horizontal asymptote. In this case, you do not. And then you would have chosen a random point to get this point right here. But you know it has to be in this quadrant because if it was in this quadrant, you would have another 0, right? You'd have another 0 down there. So that's the pre-calculus part of it. So the rules for vertical, horizontal, and holes, I have written that on the answer key for you guys, so you can see that. And so I just decided to just share the answer key with you right here so you don't have to go and look at it. So in order to find the vertical asymptotes, when we just talked about this, you want to find the values of x that make the denominator equal to 0. You also want to remember that you want to get rid of your holes, right? You want to get rid of your holes. So vertical asymptotes, your denominator equals to 0. Holes is where you have a factor in the numerator and a factor in the denominator that has a variable in it that you can cancel out. And so when you do that, that becomes, when you set that factor equal to 0, that's going to give you your x coordinate, and then you plug it into the simplified version that gives you your y coordinate. And then the horizontal asymptotes, and this is really what we're going to talk about in this lesson, this first calculus lesson, you want to compare the degree of your numerator with the degree of your denominator. The one that we just talked about is what happens when they're equal to each other. The horizontal asymptote is y equals the ratio of the leading coefficients. In that case, it's 2/3, which we have right here. If your denominator is powerful, if it's the highest degree of your denominator, then your horizontal asymptote would be y equals 0 because it's bottom heavy. And then if your numerator is greater than 0, then you do not have a horizontal asymptote. You have a slant asymptote usually, and we do not need to know about that in this class. So that was just a quick refresher on that. So I would encourage you, if you guys have not done so already in class you have, is watch the video concept on limits that we have here. This just gives you an idea of what a limit is. And then notice that the question at the bottom says, now that you know kind of what a limit is, let's start using limit notation to describe the behavior of the function above. So I'm going to go ahead and write all of this work that I would normally put in this box up here so we can kind of see what's going on. So I'm going to go ahead and pause it for a second. I'm going to get rid of all of this work now that you guys have an idea, and we're just going to look at this graph. Okay, so let's look at this graph. Now, this lesson is really on just limits to infinity. So my focus here is really just looking at as x goes to negative infinity, what's my y value doing, or what's my function in green doing, and then x approaches positive infinity, also what's happening with my green function. I'm going to also just go ahead and talk about two other things. I want to talk about what's happening here at this hole, and I want to talk about what's happening at this asymptote, because those are the only two other places where this function is what we call discontinuous, which we're going to get to in another lesson. But I want to just talk about it here just so when you guys learn those concepts, you can come back to this video and just kind of go like, oh yeah, I do kind of know what he's talking about now. So let's look at the fact that the limit, so we want to also make sure notation. So the limit as x approaches negative infinity of your function. So that's how you're going to write limit stuff out. So it's going to be the limit as x approaches negative infinity of your function. You need to make sure you write your function here because we're talking about this guy right here. So guys, this is basically saying is if I follow my green line, right, my green function, it's infinity. Remember, this is a horizontal asymptote. And in this particular example, we're not going to cross it. Okay, we're not going to cross it. It's going to approach and approach and approach this line, but it's never ever going to hit it. So this limit, as we're going to negative infinity, the y value that we're going to get out of this function is going to approach 2/3, but it's never going to get there. So as we're approaching negative infinity, our function is going towards 2/3, but it will never hit it. Okay, because limits really are the behavior of our function as it approaches a particular variable or constant in this case. So if I'm looking at positive infinity, so now I'm on the right side as x is getting bigger, I'm following my green arrow, and again, it's following really close to this asymptote, which again is going to be y equals 2/3, right? This asymptote is y equals 2/3. So again, our limit as x approaches positive infinity of f of x is equal to 2/3. So now we can always assume that if we have a function and we have a highest degree in the numerator is equal to the highest degree in the denominator. So let's say that these are the same values of n and they're the highest degree. Your limit as x approaches both positive and negative infinity of your function will always be the leading coefficients, the ratio of the leading coefficients in front of those x's. So that's very easy and an awesome simplifying trick so you don't have to waste time graphing this thing, okay? Because you don't have to graph in calculus. We don't expect you to graph in calculus because it just takes too long to do, all right? So that's the first part of this lesson. Now, if you don't care and you don't want to listen to what I'm going to say about the rest part, because this next part I want to talk about will be in a future lesson, but I want to just talk about it here for a minute, then you can just skip on to the next problem, okay? So, and I don't know, because I'm just recording the video, I don't know where that time is, so just kind of fast forward a little if you need to. All right, so let's go and look at two other points of interest in this actual graph. Well, I talk about discontinuity. And so again, I'm getting ahead of myself a little bit here, but discontinuity basically means if I'm traveling on my green line here, my green function, I can't continue over this. I call this like my little hole. It's like, you know, there was an analogy in the video you guys saw, if you watched it, is about a car traveling, and then all of a sudden we have a manhole here, right? So we can't travel over this thing. So it's discontinuous here at x equals -2. The other place where it's discontinuous is, again, if I'm going on my green line, then I have to literally pick up my pencil to come back over here. So at x equals 2, it's also discontinuous. So those are our two other points of interest that we want to talk about. And so the limit as x approaches -2 of our function, even though our function's defined as our graph is approaching -2 from the left and from the right, we're still getting this y value. We're still getting this y value right here, which we said was -1/6, right? Because our hole is at -2, -1/6. So that's another thing I want you guys to understand about limits is that when you're approaching x, this is just saying what y value are we approaching, are we getting closest to when our graph, our function approaches -2, and that answer is -1/6. And then our last little guy is a limit as x approaches 2, and so the limit as x approaches 2, and then we're going to do a little superscript here, it's going to be plus. That means that we're approaching 2 from the right, and so as you guys can see, as I'm following this graph 2, and again, we're going towards 2, right? We're going towards 2 on the right. We're following the graph. Well, that's going to take us to positive infinity, right? We're going to positive infinity, and then, we can also say it does not exist, because both of those are legit answers. And the limit as x approaches 2 from the left of f of x, well, that's going to give us, again, we're going this way, and then we're approaching x equals 2. I always tell my students the party is at x equals 2 on this street, and so this is our road, and so our road is taking us all the way down here to negative infinity, or does not exist. So we can say that this limit here, this limit of x equals 2, and I'm running out of room here, but the limit as x approaches 2 of f of x does not exist. Okay, and that's the reason why, and again, I'm getting a little ahead of myself, that the left-hand limit and the right-hand limit, or if we're following our graph to the left and to the right, they're not at the same point. All right, so that is our really simple, basic function, and really what I need for you guys to get out of what we just talked about is that if a limit is approaching positive negative infinity and our coefficients are the same, then it's always going to be equal to the ratio of our leading coefficients that are here and here. All right, so let's go and look at a couple of examples. Okay, so example number 2 is asking us the limit as x approaches infinity. So always be careful and realize what we're approaching. If this had been a value, a number, and again, we're going to get this in the later lesson, you would just substitute in. But right now it's infinity. And so we also have to say, okay, when it's infinity and it's a rational function, we want to look at the highest degree of the numerator, which it's only one term, it's squared, and the highest degree of your denominator, and it's also squared. Just be really careful, because I've seen them trick people with this. If this is an n squared and this has been n cubed, then your highest degree would be in the denominator, and we're going to get to that in example number 3 in a second. But right now they're equal to each other. So the limit of n approaches infinity of this function is going to be equivalent to the horizontal asymptote of this function. Well, all you have to do is take the ratio of your number 4 over the ratio of number 1, and you're going to get that this answer is going to be 4. It's that simple. There's no work involved in this. As one more thing I'll say about this, that this, if these are equal to each other, the limit as n approaches either positive or negative infinity, it doesn't matter if it's positive or negative infinity. I'm going to change this to negative infinity, and the answer is still 4. Because again, based on our example we showed you up here, it doesn't matter if I'm going to the positive infinity or negative infinity, I'm still going to this horizontal asymptote, right? We're approaching it from both sides. So that should be a pretty straightforward example for you guys to do. So now let's look at example number 3. Okay, so for example number 3, you guys can see it's the same thing, the limit as n approaches infinity, and again, the highest degree in your numerator is up here at 2, and the highest degree in your denominator is actually going to be equal to 3, right? So we have a degree in our denominator that's greater than the degree in our numerator. So what I want you guys to understand is you remember that the horizontal asymptote for something like this is y equals 0. So I'm just going to take a second, because I tend to do this in my classes. I always want you guys to know why it's y equals 0. The most classic basic parent function where the highest degree is in your denominator is the function 1 over x, right? The highest degree in your denominator is 1. The highest degree in your numerator is 0, because x to the 0 power is 1. And so then when you actually sketch this graph, right, if you sketch this graph, you guys will realize that, oh wait, there it is. There is a horizontal asymptote at x equals 0. And so anytime a function is what we call bottom heavy, then this answer is always, always, always going to be 0. There again is no thinking in this problem. Just like previously, if I told you guys the limit as n approaches either positive or negative infinity of our function, it doesn't matter which one. If the degree in your denominator is bigger, it doesn't matter what else is going on in here, then their answer is going to always be 0. So it's just that simple, and we love that pretty well. All right. So if it had been the opposite, if it had been the highest degree in the numerator and not the denominator, then the answer is does not exist, because we don't have a horizontal asymptote, and so it would go to either positive or negative infinity. Okay, positive or negative infinity. So let's really quickly finish this video up with these 3 examples right here on the bottom. I would suggest that you guys just pause it for a second and see what you can do with it. You guys have this. It's so straightforward. I mean, I hope it is. So take a second, see what you can do with these 3 questions, and then we're going to come back and finish this video up. Okay, so hopefully you took a look at this, and it probably took you less than 25 seconds to do it. So we're looking to the limits as n approaches positive and negative infinity. And so again, for positive infinity here, we look at the highest degree in the numerator, which happens to be a 3, and the highest degree in your denominator. Again, I look at all my terms, because again, if this has been a 4, you got to take that into account. Don't always assume it's the first term. So it's 3 and 3, and so since they're equal to each other, I know, ladies and gentlemen, that the limit as x approaches either positive or negative infinity, it's just simply going to be the ratio of our constants. Yes, it is that simple. It is that simple, that simple. So for question number 2, our highest degree is in the numerator. So now you can say that it does not exist, but let's say this is multiple choice and does not exist is not an answer. Let's say your answers are 0, 1, positive infinity, and negative infinity. All right, then what do we do with this? So what you do, and this is just our little side note stuff, is you take the ratio, so what I've circled here, and you simplify it. You simplify this and you get x over 2, right? So I canceled out an x squared on the top, x on the bottom. So I'm going to just say that this is going to be y equals 1 over 2x. So this is the slant asymptote, the general idea of what the slant asymptote of this function is going to look like. So when you graph the function 1/2 x, the 1/2 really doesn't matter. All that really matters is that you have a positive slope. So we know that this function is going to actually be really close to this line. So as x approaches infinity, it doesn't matter if I'm going this way with it or this way with it. If I'm approaching positive infinity, notice I'm also going to positive infinity. So this answer is going to be positive infinity. If this had been a -2 here, and this had been -2, you'd have done your slope this way, and then if I approach positive infinity, if I'm going in this direction, right, if I'm going in this direction, and I'm going to positive infinity, then I'd actually be approaching negative infinity, which is right here. So this is the only time where this really does matter. If I had changed this to where x approaches negative infinity, then we would take this graph and we look at it from this direction, right? So negative infinity would be negative infinity. So that's the only thing that you're going to have to worry about. But I will tell you, if it's not multiple choice, ladies and gentlemen, to save yourself some time and energy and write does not exist, that is a legit awesome answer to do. And then finally, for example, number 3, we are bottom heavy. Okay, we are bottom heavy. And so the highest degree is in the denominator. And since that's the case, there is no thoughts at all. The answer is equal to 0, as it always will be. Okay, again, it does not matter if this is positive or negative infinity, the answer is always 0. So that's the first introduction of rational functions to limits. In the next video, I'm going to talk about other functions that are not necessarily rational, parent functions and stuff like that. We'll do that in the next video. So I'll see you guys in video number 2.